Traditional engine control, open-loop mechanical engine controls were used to manage air, fuel, combustion. Electronic engine controls, fuel injectors and motor-driven air controllers replace carburetors. Crank position sensor and ECU replace points in distributor. Multiple spark coils replace rotor and distributor cap. Engine Control Unit, ECU, manages all electronics devices. Oxygen sensor and ECU monitor exhaust for controlled emissions. An Engine Control Unit, ECU, also commonly called an Engine Control Module, ECM, is a type of electronic control unit that controls a series of actuators on an internal combustion engine to ensure optimal engine performance. The ECU module includes microcontroller, analog driver circuits, air by fuel filter control, feedback control through various sensors.
Electronic Control Unit, or ECU. The ECU is a microcomputer. It's constructed from printed circuitry and contains a large number of electrical components, including many semiconductor devices. Its input devices receive data as electrical signals. They come from sensors and components at various locations around the engine. Its processing unit compares incoming data with data stored in a memory unit. The memory unit contains basic data about how the engine is to operate, and an output device pulses the electrical circuit of the solenoid-type injection valves. It is normally located in a safe place behind a kick panel in the footwell, under the passenger seat or in the boot, and connected by a multi-plug or plugs to the vehicle's wiring harness. The core function of a basic ECU in an EFI system is to control the pulse width of the injector. More sophisticated models also control other functions, such as idle speed, ignition timing, and the fuel pump. These wider systems are called engine management systems. The more precise control they allow is very effective in reducing fuel consumption and exhaust emissions. The ECU adjusts quickly to changing conditions by using what are called programmed characteristic maps, stored in the memory unit. They are programmed into the ECU just as data is programmed into a computer. Characteristics means the engine's operating conditions, and they are called maps because they map all of the operating conditions for the engine. They're constructed first from dynamometer tests, then fine-tuned to optimize the operating conditions. This data is stored electronically. Ignition timing is crucial in this process. Between one spark and the next, the ECU uses data it receives on engine load and speed to determine when the next ignition point will occur. It can also correct the map value using extra information such as engine coolant temperature, intake air temperature, or throttle position. Putting all of this together, it arrives at the best ignition point for that operating condition.
Engine control modules are almost always located in a dry, secure location, and many are mounted under the passenger side dash. But there are only so many places in a vehicle that offer the moisture protection necessary. The Engine Control Module, ECM, controls all the engine functions to keep it running correctly, monitoring all the sensors of the engine. The Powertrain Control Module, PCM, controls the engine, like the ECU, and the transmission, like a TCM. By placing control of both the transmission and engine into one unit, the PCM can better coordinate their functions for better power delivery and fuel economy.
Settings are made for various operating conditions according to fuel consumption, engine torque, exhaust emissions, knocking tendency, and drivability. That means, for example, that starting ability can be improved by making timing during cranking depend on cranking speed. Timing at low idle speeds can be set for low emissions, smoothness, and fuel economy. For part load operation, the emphasis is on economy and drivability. At full load, it is set for maximum torque without detonation. Using the digitally stored map, the ignition point is set for each operating condition, without affecting the settings for any other condition. All of this raises an engine's overall efficiency for all operating conditions. Corrections to ignition timing, combined with those to the injector opening time, provide the optimum values to achieve the best combustion. With higher compression ratios, there is more risk of detonation and damage to the combustion chamber. A knock sensor allows ignition timing to be calibrated to achieve the best settings for normal operating conditions. Knock or detonation can then be eliminated separately using closed-loop knock control. When a detonation signal is received, the control unit retards the ignition setting to bring detonation under control. A turbocharged engine is different. Simply retarding the ignition could increase the already high temperatures at the exhaust-driven turbine. But reducing the boost pressure at the same time brings detonation under control quickly. As soon as knocking is detected, ignition is retarded, which works immediately. Reducing boost takes longer, but as soon as it takes effect, the control unit returns ignition timing to its optimum value. The control unit can also control other output functions, such as engine speed limiting. When actual engine speed reaches a programmed maximum, the fuel injection pulses can be suppressed. This protects the engine from over-revving without disadvantaging its operation. The ECU can control the fuel pump. For safety reasons, when the ignition is turned on and the engine is stationary, the fuel pump operates for a few seconds only, enough to prime the engine for starting. It starts again during cranking and when the engine is running above a specified minimum number of revolutions per minute. Some exhaust gas is allowed to recirculate to control the nitrogen oxides. How much exhaust gas does this can be controlled by vacuum and vent solenoids in the vacuum circuit of the EGR valve. When loads are put on the engine, such as from air conditioning or lights, the control unit regulates how much the idle speed control valve opens to maintain a preset idling speed. Fuel vapours stored on the active material in the canister are drawn into the cylinders and burned when engine operating conditions allow. At different engine speeds and loads, the control unit operates solenoid valves that alter the effective pipe length of the manifold. This extends the torque output over a wider range of engine speeds. The cooling fan is switched on automatically when the air conditioning is switched on. Instantaneous fuel consumption can be displayed on the instrument panel in front of the driver. The check engine lamp is a warning light on the instrument panel. It is lit up by the control unit to warn of malfunction in engine management. The check engine lamp can also indicate fault codes. They can be a series of lamp blinks or voltage pulses from the control unit. They give a number for the kind of fault that is occurring. One lamp blink, followed by a pause, then 3 blinks in rapid succession, indicates code 13, which may mean, for that application, that the oxygen sensor voltage is not changing, leaving the engine in open-loop operation. When the control unit does not receive a signal from a component, it uses a substitute value from its memory bank. The engine may still operate near its normal level, and the driver may not realize a problem has occurred. In some cases, if the fault is in a major component, the control unit may go to a limp home mode, with a fixed injection duration and ignition setting. The vehicle remains drivable, but with reduced performance, allowing it to be driven to a convenient service point. With a data scanning tool, an engine management function can be viewed. All of these functions together are a snapshot of the state of all inputs and outputs at that instant. This data can then be analyzed. A control unit can use data from its memory to adjust engine settings over time. This is called adaptive learning. It only occurs with feedback or closed-loop operation. This vehicle is using medium throttle with light loading and mild acceleration. Its control unit will set fuel delivery for a specified pulse width. However, if fuel pressure is less than when the vehicle was new, feedback from the oxygen sensor can cause the lambda control to increase injection time. The control unit learns the new time and stores it in its memory for future use in that condition. If the battery is disconnected or memory is lost, the settings revert to the manufacturer's programmed specifications, and the vehicle then has to be driven in a range of conditions to let the control unit, in effect, relearn the engine's fuel settings.